Okay, now we're ready to implement a generic hash table that can handle just about any type of item that we would like to store in it, and do so in kind of a generic fashion. And we're going to use templates to support this. So we're going to define a generic hash table class that takes the key and the hash function as template parameters. And the key will just be the type of object we want to hash. The hash function will be a functor object that we use to specialize our template. And we're going to use linear probing for this implementation. Okay, so to start with, we're going to specify that this is a template and that it's specialized, needs to be specialized based on key, which is the kind of object we're going to store in it, and the hash functor, which by default, we're just going to say is a standard hash created from key. Now, this will only work if the key we provide, right, this default value for hash will only work if the key is like a primitive type or some type that hash already knows about. And so if it's some special type object that we make ourselves, we'll have to also write our own hash function for it. But for ints and strings, we won't need to do that because we can just reuse standard hash. Okay, inside my HT class, my generic hash table class, I'm going to support linear probing, so I'm making a enumerated type that I can define empty since start to be -2, empty after removal to be -1, and valid equal to 0. And I'm going to use these. I'm going to use these values in the implementation. I define a struct bucket to include a status, which is one of these values, and a key. And then when I initialize a bucket, I initialize it to be empty since start. Okay, and then I'm going to have my table, which is just an array of buckets. And then I need to track the size of that table. I need a hash function of type hash. That's one of my template arguments. And then I also need a probe distance. Okay, then my code is going to kind of look like this. In my constructor, I'm going to allow my object to be initialized by specifying the size of hash table I want and by specifying the probe distance. And so after I specify the value of m for the size, the constructor needs to allocate an array that's that big. It also needs to initialize the size member and the probe distance member. So the rest of the code works. And then this insert function is basically just like the linear probing insert function we've already talked about. The only difference here is that I'm going to use that hash functor to calculate the index. So I pass in the key object into the functor and modulo by the size in order to get the index. And then the rest of this code works exactly the same way. The htfind function, also the same thing. I use the hash functor on the key object that's passed in as an argument to calculate the hash index. I modulo by the size to make sure it's in the range of the table. And then down here, in order to find this key, I have to compare, anywhere the entry is valid. And actually, I need another check. I need to ask, is the entry valid? And the data is key. So I have a slight mistake here. I need an and here. So if table index.status is equal to valid, and the data stored in that entry is equal to key. Now, one other thing I want to point out here, this equals, this gets invoked on a key type object, which means either this needs to be a primitive type for which the language understands this operator, or we need an operator equal implemented on our object so that the compiler knows how to do this comparison. Okay, and then finally, remove is also similar. We use the key object and the hash functor to calculate where it's going to be, and then we do our same kind of linear probing to look for the item, and if we find it, if we find the key, then we set the status to be empty after removal. Okay, now here's an example of how we can use this object. I can declare my hash table to have integers. I'll call that H. Or I can define my hash table to have strings. I'll call that S. And note, if you remember, my hash table takes 2 arguments, but if my key is a standard type, then the hash argument gets set by default to be the standard hash, parameterized on the key. So for ints and strings, that's going to happen, and I'm just using the standard hash for my hash table. And so for my integer hash table, I can insert 5 and 100. For my string hash table, I can insert hello, and then I can search for hello and see if it's in there. And if you run this code, it'll work and we'll properly find hello. And you can find this code in my GitHub repository under week 6. So you can run this generic class and try it out yourself. Okay, we can make the hash table object more configurable as we did here by making the key type generic and by making the hash function a functor object that we use to specialize the table. The only constraint on this code for it to work properly is that the key supports operator equals equals, and that hash has an int operator defined for the key type. And as long as those 2 things are true of those 2 objects, so key has a comparison operator for equality, and hash has a function call operator, as long as those 2 things are true, you can specialize that HT object and it should work.